not to know. No, it's difficult. Instantly, it takes time, experience. So, few words more about time domain. Only few more words. Literally few. As you noticed yesterday, Mr. McNeil and I gave few examples. These examples, first of all, I gave example, earliest example, outlining oil-water contact. Let me tell you, it happened somewhere at the beginning of 70s, but still this method in East Siberia is used for outlining oil-water contact, not only in reservoirs, but in the exploration together with seismic. Because in seismic, very often, it's when we have gas or oil, there is attenuation of the waves. Blind spot, it's called. And so, using method of reflection waves, we get some indication of presence of gas. However, sometimes coefficient of attenuation, not coefficient, the attenuation is not very strong. So it's natural to use approach which is often widely used in mining exploration, integrated geophysics. So the application both reflection wave and time domain method does not increase essentially cost of the service. So measuring attenuation, we have one parameter which indicates presence of gas. Measuring time domain, increase of conductance around the zone, tells about where water or where could be gas. So it became very standard procedure in the areas where relatively resistive environment. This method, but what I showed you, will not work as soon as total conductance of upper section is less than conductance of salt water. It's natural limitation. Nothing wrong. Now, in this fact, now, when this result was obtained, when it was used, of course, in West, there were attempts to use it for hydrogeology. Duncan McNeil showed you natural application of this concept to hydrogeology. When we have salt water, physically it's this, from principle it's the same, only scale different. Before I spoke about depth 2,000 meters, here depth 100 meters. Now that's one point. Point number two, all these examples could create incorrect impression that transient soundings is used only for the cases when there is salt water. For instance, after we left, I recalled case which was performed by the same company, Black Hawk. It's located in Golden. I consulted this company. I helped to produce these methods in this company. It's one of the best companies in environmental geophysics. It's the largest company in environmental geophysics. It's a Black Hawk company, and president of this company, Dr. Peter Hoekstra, very close friend of Duncan McNeil, mine. And it belongs to huge corporation, huge engineering corporation, Coleman, does not have any relation to geophysics. It's located 2 miles from Golden, 1.5 miles, I don't know. Very, very, very close. This company is simply uses shear waves, P waves for in engineering problems, time domain, magnetics. So it's a very good example of company which uses integrated geophysics. So this company, many, many years ago, maybe 10, was asked to map permafrost. So completely different target, no more salt water, and time domain method was used. That's onshore or offshore ice. No, I took wrong piece of, just a second, of chalk. No? That's ice, that's water, ocean water, and then, just a second, vice versa. Permafrost. Now, it's a very resistive section, very resistive, that's very conductive, so water, ocean water, shallow, 50 meters, 100 meters bottom, resistive material, again conductive material. So it was important for seismic, because in seismic one of sources geological noises is this kind of resistive materials which forces to make static correction against static effect. So in order to know how to make static effect, onshore, offshore, it was important to map this not conducting water, opposite, resistive target. And again, on the ice, we perform soundings in direction perpendicular to coast, and it was a three-layer curve here of type not H but K curves, K because intermedium layer is resistive. So I only would like to mention about this method because transient soundings could be used for different geoelectrical conditions, where target either is conductive or resistive, as Schlumberger method. That's one comment. Couple more comments. When we perform soundings, rho 1, H1, rho 2, H2, rho 3, and there is inhomogeneity, swamp, clay, field fraction zones, those are different sources which create lateral change resistivity in this direction. Time domain has interesting feature. It makes it different from any other methods. At early stage, this inhomogeneity makes influence, no doubt. It distorts curve apparent resistivity, no doubt. However, with increasing time, due to the fact that it's a diffusion, no currents here. So starting from certain moment, influence of upper section disappears. If you remember, we discussed it. If we have two-layer medium, rho 1, rho 2, there is a moment when upper layer becomes transparent. What does it mean transparent? Influence of induced currents is very, very small. So it doesn't matter it's uniform layer or not uniform layer, results remains, unlike other methods, the same. So influence of the up surface geological noise decreases with increase of time. It's used also. Now, that's one second comment. I think last comment about time domain, and then I will go to completely different, we'll start to discuss completely different subject. Oh no, two more comments. I look table, two more comments. let us take typical model in mining prospecting. Conductor and overburden. And high resistive host rock. It's not necessary, but let us do this case. We perform measurements. What do we measure? We measure effect due to overburden. We measure effect due to conductor. And our goal to approach to the late stage when conductor manifests itself in the best way. Also exponential decay, we can define time constant. In most cases, in most practical cases, most, not always, at that moment, field due to overburden is also corresponds to late stage. So we don't know conductance, we don't overburden, we don't know how it thickness, we don't know how it changes. It's a source of noise. But what we do know, often, not always, again, not always, field which we measure, or electromotive force, is some effect due to our body plus effect due to noise, due to overburden. Again, we don't know conductance, we don't know thickness, conductivity, but we know we are approaching to the late stage. Therefore, there is some coefficient A which depends on conductance, on geometry, divided by T cube. That's what we do know. We know, regardless what is the thickness, conductivity, as soon as it's late stage, field must decay in this way. So I saw reasonably many examples in East, in Russia, when performing measurements at two times let us take these measurements and time sometimes T2. Just a second. It's equal C E minus T2 tau plus A T2 cube. Let us take another measurement. We have them when we measure transient response. Again, we don't know this coefficient. It's a noise. But we know how it behaves with time in most cases. So if you, that's enough. So if you multiply this term T2 cube, T1 cube, it takes difference, not difference of values of the field, but before please multiply this coefficient. What would happen here? Here a difference between T2 cube will allow not to remove noise, but reduce noise. It's a difference. Now, so it's some kind of filter which is not, which is based on understanding behavior of transient response due to overburden. Now, do I speak clear? Now, often we have, again, we don't know this function. It's unknown. It changes from point to point. Here, one value A, another value B. But what is important, we do know dependence on the time. It's not constant, a function of point of observation. It depends on size of the loop. It depends on many, many factors. But there is one important factor. Regardless what is the overburden, always there is a moment when field will decay, magnetic field derivative, therefore T4 will decay in this way. So combining our information about behavior of the field due to conductor and layered medium, we can subtract, we can reduce, sometimes even greatly reduce. So it's you have data, and that's one of the way of working with this data in order to remove noise. That's one example. It's natural if there is no overburden, but there are host rock. Simply, we also know, suppose no overburden, but there is a finite resistivity of host rock. Then you will know field is equal, again, some unknown useful signal, plus, again, unknown different constant, not the same, only letter the same, T over 3 half. Performing the same procedure, we can again reduce, not remove. Nothing can be removed, only reduce if we are lucky. It's one lucky, if it's a favorable conditions. But what is the trick of this, trick or basis of these methods? It's based on behavior of the field. Therefore, it does not require knowledge geology as soon as we know we feel that we are late stage. If without late stage, it means it will not work. That's all. Now, combining both, we get situation when we have unknown overburden, unknown host rock, we can, having data, we don't need additional data. No, the same data, only we are working with different channels. That's what I wanted to point out. That's second or third comment. Now, let me Of course, the same applied for horizontal component of magnetic field. I only choose examples. Now, last comment. I very briefly, at the beginning, mentioned about time constant. Now, I would like to speak a little more detail and show you how time constant changes for different conductors. So, I gave you case for sphere. Time constant equal gamma mu naught a square over pi square. Then let me show you what happens with disk. Sometimes, suppose we can replace our body by a metric thin disk. If its conductance S, it means thickness times conductivity, then time constant equal mu naught SA times divided by 5.5. What is the A? Radius. Conductance is S gamma times thickness. So time constant is governed by conductance and radius or size in direction perpendicular to the field. Why I say perpendicular to the field? This time constant is independent how field is directed. But if you can mentally, that's your primary field, your field can be presented as field along disk and perpendicular. Along disk, if you consider field along disk, since it's a very thin, it does not practically create any induced currents. So you can say, not to say, it takes place, time constant equal mu naught S A divided by 5.5. Let me give you another example. Suppose we have cylinder, very long cylinder, doesn't matter how field directed also, constant equal mu naught gamma A square divided by, let us say, 6, more precisely 5.78, but 6. Now, you see how everything was 10, 6, 6. So there is no any strong change. Only we have to know what parameters which define. Let me give you another example. Plate. Conductance S, again, thickness times conductivity, very, very, very long. Now, that's 2A. Conductance, I gave it once, and now I'm showing you together with other parameters, divided by 4. When thickness H much smaller than this dimension. Now, let us look at another example. Suppose I have thin plate, but cross-section changes as elliptical cross-section. And again, that's B, that's A. Now, suppose field has arbitrary direction, but not along. Not along. So always there is a component magnetic field in perpendicular direction. Then time constant equal mu naught as A divided by 5.1. Now, suppose very unpleasant case. Suppose our elliptical cylinder vertical and our primary field down. Let us assume we created field in this way. Our loop is located above vertical dike, at dike. What do you think? What happens in this case with time constant? It will be large or small. Very small, very small. And then time constant is equal mu gamma mu naught as B divided by 3. B, it's a half of thickness. So, two troubles instantly. Trouble number one, field going in this direction. Cross-section is small. We do have induced currents, but they are small. Moreover, time constant is extremely small, so decay would happen quickly. In general, time constant is independent how oriented body, but that's extremal case when field exactly along major axis. Now, let me take another conductor, and then I will fill this part. It will be done. Suppose we have spheroid with axis B, axis A, conductivity gamma. What happens with time constant when ratio between A and B changes? First of all, let us assume that we have very almost disk with elliptical cylinder. Let us call thin tau B equal mu naught SA divides 7.7. Now let us compare what would happen when we start to change A over B. It turns out if A over B equals 32, so axis A 30 times greater than B, 1 meter and 30 meters, then our field has some arbitrary direction in this way. Then tau constant of this real shaped conductor with finite thickness more precisely, tau over tau B is equal 1. So no difference. If we take ratio 16, A over B 16, 1 meter, 16 meter. Practically no difference. 0.94. For all practical purposes, it's the same. Now, if we take even A over B 8 meters, 1 meter, then tau over tau B, it's around 884. So again, small difference. All these spheroids behave as you had very thin body. Now, let us take ratio A over B 4. Again, tau over tau B equal 0.7. Not great difference. Not great difference. And finally, when you took A over B 2, it becomes equal tau over tau B equal 0.56. Only 2 times decrease, so it's a very stable parameter. Now, I gave you already a thin conducting plate for finite dimension, so let me stop here. So some general pictures. That's all about time domain, taking into account what was told before. Now let me discuss with you completely different subject. It has straightforward relation to relation between geological noise and useful signal. As I told you, I am looking on all in the past, in the process of improvement electrical methods. So as I told you, somewhere in up to 50s, there was only electrical method for soundings, for mining prospecting, not in conditions when Canadian shelf or Scandinavian, but in environment where we have overburden, host rock. There were known 2 facts about electrical methods. 2 facts. Fact number one is, as I told you, I have 2 conductors. If they greatly differ by resistivity, anomalies practically the same. So if rho 1, 100 ohmmeters, here 10, anomaly is almost the same. So poor resolution. Then it was known the second fact, about which I didn't mention yet. There is almost iron rule, almost. When you use different profiling systems, not electromagnetic, A, M, and B. I'm talking about A, M, and B. I don't understand why I show you such high mountains. Now, if we have conducting overburden with thickness H, and we have ore body types of the dikes with thickness H small, and we have again our array M and B, then rule of thumb, regardless of conductivity of the dike, regardless of what is the conductivity overburden, as soon as it's less than resistivity of host rock, you cannot detect your conductor if thickness overburden more than 4, 6 thicknesses of this dike. So it's a very serious limitation, extremely serious limitation. You can make your separation AB as far as you would like. No use. For instance, you can use dipole system. B here, Mn. So here, generator. Here you measure voltage. It's also profile systems. You can fix position AB, move Mn, will not help. Why? Number, first of all, that shows solution of forward problem show and experience show. But what is important? Yes, if you make large separation, you can create currents here, no doubts. That will be currents, charges, electrical arrays. But if there is overburden, these charges induce other charges at interfaces, and they usually screen all effect. So that's the rule. So if you have only thickness of dike 3-4 meters, don't expect to see it and the depth 20 meters, regardless how huge your separation. So that's these two facts were known. So when inductive method began to use in a conducting environment, non-conducting they were used before Second War. Sweden developed excellent Slingram systems, Canadians. So it was a lot of equipment, but in the West there were no experience in conducting environment. There were sufficient places for working in resistive, very favorable conditions. But when there were made attempts to use in conducting medium inductive methods, loop for instance, it turned out it's possible to detect deeper, unlike electrical methods. So it was a very good period of time. First of all, if you remember, measuring quadrature component at low frequency part of spectrum. What is the ratio between here tau noise, tau ore body? If you are working at low frequency part of spectrum, your magnetic field is proportional tau. So you have better resolution. If you are working in measuring in phase component, even ratio better. So it was excellent, short but excellent period in, it's, I would call, optimistical period of inductive methods. I remember time, I remember papers, I remember many other things, and which finally we developed method which has higher resolution than DC methods. So it was driving force in developing inductive methods. I'm talking only in frequency domain now, then time. So, but evil didn't sleep. And we didn't notice that it was sometimes, in spite of the fact no more grounded line, there is still different source of the fields which much less related with conductivity of our body than we expected. And that's what I'm going to discuss with you, what I mentioned, Duncan mentioned, and then I will discuss more detail this subject. So let us do the following. That's conductor. That's loop. Let us imagine experiment. That's conductor, arbitrary conductor, free space, and there is a current loop. No more grounded electrodes, nothing. Our current loop with frequency 1000 Hz. Let us think, what would happen? What do you think? So you have generator, it generates current, and my question is, what happens on the surface and inside of conductor? So we will have change of magnetic field, correct? That's so, therefore what would arise? Induced currents. What else? What else? So I take example which far away from real conditions. I would say I consider example which you can reproduce only in laboratory when you test your equipment. So what would happen? These induced currents would create secondary magnetic. That's I understand. So no doubt we will have primary and secondary field, but it will be something else. We overestimated intelligence of currents. Let us look together. We have conductor, free space, and our loop. Our current changes I cosine omega t. This current creates what? Primary magnetic field, cosine omega t. This magnetic field creates what? Primary electrical field. That's the main role in frequency domain all time, in time domain during REM time. creates primary electrical field. So we have primary electrical field, for example, some current loops. Now, we have conductor. Here there is a primary electrical field. Here, 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 etc. When we have primary electrical field, what would happen? Current arises. Charges start to move. So they move under action of primary electrical field. So this ion or electron starts to move, and then it reaches what? Surface. Because primary electrical field going through surface. Tell me please, this charge will go into air or not? No way. What happens with this charge? It starts to move along, it changes direction. Currents can move only inside of conductor. So something must stop these charges. They are not clever. They can stop only if there is a reason here, cause, to create electrical field in opposite direction. Then they will not move. They will go around. And this reason is surface charges. I told you at the beginning, even I gave you expression, density of charges equal to epsilon naught K12 E and energy. So, back to our piece of metal. If I have a loop, then primary electrical field intersects surface and here electrical charges arise. When they don't arise, only in very special case, when you have circle loop and your conductor exactly beneath and it has cylindrical surface or sphere, then primary electrical field does not have normal component. So in all practical cases, charges arise on the surface of the conductor. Well, they rise, they have one function. They create such electrical field that your induced currents only inside. They cannot move outside. That's physics of our effects. Time domain, frequency domain doesn't matter. It doesn't matter. Now, when you have free space, these charges only affect on induced currents, geometry of induced currents, and we don't feel them. Why? Because these charges don't create what outside? They do create electrical field, but they don't create current. They don't create current, and therefore they don't create magnetic field. These charges are sitting on the surface. They change with frequency 1000 Hz. They do create strong electrical field, but we don't use line MN. So we measure magnetic field, but magnetic field caused by current. Therefore, we don't feel these charges. These charges, as in DC current method, are sources of electrical field, only alternating. In time domain, the same story. So, as soon as surrounding medium is insulator, no problem. But as soon as surrounding medium is conductive, these charges will perform their evil work. And they create currents which will go through our body and through surrounding medium. This part is called galvanic part of the field. Galvanic, it means related with charges. So, therefore, magnetic field consists in general two parts. Magnetic field caused by induced currents and magnetic field So let us continue. Let us take as example isometrical conductor. Now let us place it into conducting medium. Gamma 2, gamma 1. And there is a source, loop, for instance. We will consider several types of sources. Loop, electrical dipole, and plane wave. So when it was realized that electrical charges arise on the surface, that was shock, because we wanted introducing inductive mining prospecting. It was hope, no charges, no weak, poor resolution, everything would be much better. It was really shock. Now, since charges arise, therefore, two currents pattern. One current arises inside of conductor. And behavior of this current is described known function omega tau unit. Just I know we don't use complex numbers. Sorry. So behavior of the currents inside is equal to some omega tau unit plus omega square tau square cosine omega t plus omega square tau square unit plus omega square tau square sine omega. That expression describes induced current inside of conductor. They depend only time constant, and therefore magnetic field caused by these currents also depends on time constant. That's the best part of electromagnetic field. That was we wanted. However, there are currents, there are charges which arise at interface. There is conducting medium. Instantly, electrical field causes current through conducting medium. And it turns out there are cases when this current does not depend on conductivity body at all. There are cases when it does. For instance, if it's a spherical conductor or close to isometrical, conductor. Currents which arise here is independent on conductivity of conductor. For instance, magnetic field causes any component of magnetic field, caused by this current, let me write letter J, galvanic, is proportional conductivity of one surrounding medium. If it's a symmetrical conductor, it's equal gamma 1, gamma 2, divide gamma 2, only, vice versa, but doesn't matter, because I only show idea. Gamma 2, gamma 1, gamma 2 plus 2 gamma 1, proportional size of the body, square distance, and proportional primary electrical field. Now, what is written here? This coefficient practically is independent on conductivity of our body. Because this coefficient, it's easy to see, if ratio of large, then it's almost 1. What is it? Conductivity of formation. So, this part of the field practically is the same over poor conductor and good conductor. So we return back to our past. Of course, there is another part of the field, vortex part of the field, which is caused by these currents. Here, situation is better. It's proportional, for example, quadrature component of the currents, primary magnetic field, cosine omega t, some coefficient d, depends on geometry, d1, omega squared, tau squared, unit plus omega squared, tau squared, d1, again primary, sinus omega t. So we thought we have only these two terms when inductive methods were developed. Again, this part of secondary field is caused by only induced currents inside. This part of the field is caused by currents going through surrounding medium and back. They present due to these charges. So we have two fields. B equal B vortex plus B galvanic. Now, if it's not clear, please ask me. Now, when, if you don't want to ask me, or feel uncomfortable, let me ask you a question. When this part of the field is absent? Free space, one situation. What else? Yes, very good. So, for instance, if we create a symmetrical body, loop, and primary electrical field tangential, there is no such field. So loop is, speaking strictly, very good generator, because it's trying to at least to be tangential body, or it creates positive, negative charges, and they cancel each other, not completely, but in good extent. So each time when you create it, but still do create charges, no doubt, there is still galvanic part of it. Also it's clear with increasing resistivity, decreasing conductivity surrounding medium, density of these charges becomes smaller. So, but when more conductive medium, we are in trouble. We are in deep, deep trouble. So we have three fields. One, in phase if quadrature if current changes sinus omega. Here, quadrature if current changes sinus omega t, for example. That's in phase component plus this component of the field. Everything when I'm speaking in terms of frequencies, it's transformed into time domain. Now, when it was realized, it was unpleasant shock. Very unpleasant shock. I remember this time very, very, very well. Also, as soon as it was realized, that was beginning of big concern in magnetotelluric methods. And finally, this fact brought to collapse magnetotelluric exploration method. Only this fact, only. Now, I will come to this point. So, if you understand physics, let us ask ourselves, when this part is small, when this part is large? Partly we have answered this question. When medium is resistive, we can expect this part of the field is small. Now, what else? Primary field. Here, vortex part of magnetic field is related with proportional primary magnetic field rate of change with time. Here, proportional primary electrical field. At different methods, completely different relationship between primary electrical field and primary magnetic field. Let me give you 3 examples. If we have loop, dipole, if you remember, dipole. If you remember, I wrote expression for magnetic dipole. BR, primary field, R component of primary field, equal mu naught M 2 pi R cube cosine theta. And if current changes sinus omega t, I have to write sinus omega t. What about electrical field? That's primary electrical field. That's the field here. What is it? It's equal I omega, we don't need I, omega mu M naught 4 pi R squared sinus theta cosine omega t. So let us compare these two expressions. Electrical field is proportional to frequency. The low frequency, the smaller this field. So at low frequency methods, usually this part is small. Why? Because we are using our loop and the electrical field arises inductively as a rate of change. Low frequency, low rate of change, low inductive part of the field. Again, I don't describe, again in my book there is a chapter well, it's called galvanic party. I was young as you are. I published 3 papers by chance in 61, 62. They called influence surrounding medium neutral source. Second part was called influence of surrounding medium far away. And third paper was called 3 methods of excitation of the field in inductive mining prospecting. And it turned out, I didn't expect, because I discovered this unpleasant effect, and it turned out it was beginning of, for example, disaster of MT. If you read sometimes about MT, you will find reference on this paper. So it was nothing from mathematical point of view. I took very known solutions which were done by great masters, theory, Summerfield diffraction on the sphere, who knows. But I only took parameters which correspond to our geological conditions. I got all these simple formulas. Formulas were not interested for me, but it was important to see these bad charges. So, anyway, so in inductive methods, at least we see decrease of frequency can decrease influence of galvanic part of the field. Now, let us take electrical dipole. There are some methods in electrical methods which use grounded line. Suppose I decided instead of loop to use grounded line. A, B, electrical dipole. What creates in this case primary field? What do you think? So you take wire, again 1000 Hertz, and put 2 electrons. It looks like, what is the difference? Created strong current, rounding, strong current, good shape. Since I made strong, powerful source, even I can measure far away from, close. Let us look what happens with electrical field and magnetic. First of all, what creates electrical field in this case, first of all? Charges which arise if we take uniform half space. That's A and B. We have here charge AA and AB, plus and minus. And using formula direct current, we can write electrical field, for example, ER equal some moment divided by 4 pi r cubed cosine theta cosine omega t for it. So, and the same for E theta. What is essential? Here, primary electrical field was proportional frequency. So decreasing frequency, we decreased effect because it was inductive electrical field. Here, magnitude is independent on the frequency. It's a constant. Now, what about magnetic field? Magnetic field, also independent on the frequency. But usually, if you recall formula, you will see that magnetic field cosine square r square, some cosine omega t. You will see that magnetic field is relatively small. And therefore, this part of the field will be dominant. It means that measuring magnetic field caused by grounded excitation, galvanic part of the field prevails. In essence, it means that we repeat everything what was done in DC method. It's not too bad. It's not too bad. It's not good, it's not too bad, but sometimes it could be very good. Let us clarify this general statement. We found out that electrical methods have extremely poor resolution. Poor. Good conductors, bad conductors create almost the same anomalies in geometry, the same. So we have to understand this fact to say electrical methods can be extremely useful in mining prospecting if we perform mapping. Don't pretend that we would like to distinguish anomalies by conductivity. We would like to map zones, for example, zone of where we have increase of overburden, for example, drastical, as Peter mentioned me a few minutes ago, or opposite. So electrical method will map reasonably well, could map reasonably well these structures. But we will not be able to say what is the conductivity of this zone. However, as soon as we use grounded line, due to this factor that this field is independent on frequency and leading, galvanic part of the field prevails. So we have to forget about all time constants, determination of all time constants, about vortex effect, because usually, not always, usually in most cases, it's relatively small. Now, so that's second step. Third step. It's simple matter to show the same story with receiver. With receiver. If you have receiver, you have two choices in receiver. Either measure magnetic field or measure electrical field. Amen. If you don't have galvanic part of the field, you don't have charges, doesn't matter, you can use it. So in ideal classical model, when no charges, only vortex currents, the result is the same. But as soon as you have change of resistivity, charges which arise here, or you have simply some zones of low resistivity, confined zone resistivity, electrical field drastically emphasize galvanic effect. So the fact that in all normal, regular industrial methods, nobody measures electrical field happens not by chance. It happens because, not because it's easy to measure magnetic field, because we are scared to get method which would be similar again from point of resolution as DC methods. So that's the reason why we use inductive excitation and measure magnetic field. Now, again, if we are not interested by resolution, I would like quickly to perform mapping, no problem, but we have to bravely say we know our resolution will be poor. Later we can put more accurate methods. And finally, regardless what is the method of excitation, grounded line or loop, if it happens that we measure relatively far away from transmitter, we are working in a very special zone, which has name, the wave zone. I bravely mention when I consider magnetotelluric for some reasons which I don't remember now. Now, let me show you what happens in this case. Again, today it's some kind of review of some aspects. It's only, maybe you will remember. That's all. Now, regardless what is the transmitter, AB or loop? Size is not important. What is important? Okay, shock doesn't work. Now, I know why they don't work. They ask me to stop. Okay, so if point of observation R is such that R distance greater than 2 pi delta or greater than wavelength, then we are working with so-called wave zone. I mentioned it, Duncan mentioned it. So energy goes in this way as a plane wave. Plane wave. And in this case, there is a peculiar relationship between electrical magnetic field, regardless what is generated. It could be vertical line as VLF in radio station for VLF. It could be ionospheric sources. It could be grounded line in control source MT or in any other method. It could be loop, no, doesn't matter. Horizontal loop, horizontal line, vertical antenna, doesn't matter at all. Iron rod. In this case, there are two, in ground, there are two components of field, mainly in ground, electrical and magnetic. And ratio between them is proportional coefficient, which is omega mu divided by rho. It's impedance. That's impedance in uniform half space. So electrical field which creates charges, is proportional resistivity, square root resistivity, omega mu conductivity, inverse proportional resistivity, times magnetic field. This is the relationship between primary electrical and magnetic field. And all calculations show, for all practical purposes, if you have conductor, good conductor, poor conductor, and it's placed in such field, galvanic part of the field much higher than vortex. So it means you are in deep, deep, deep trouble. From point of resolution, not from point of detecting. We have to distinguish, because geophysicist has to clearly understand, to my knowledge, what he wants. When he wants to perform mapping, no problem. When he wants to distinguish good conductors from poor conductors, completely different story. So there are three zones, and the most favorable zone where we are working with time domain and frequency domain, loop inductive excitation, and we measure also magnetic field, not electrical. So again, iron rule is don't measure electrical field, don't create electrical field due to electromagnetic field due to grounding line, because otherwise you make resolution worse. Don't measure in wave zone. Now, there is a last moment in this review. Is how shape of the conductor affects on galvanic part of the field. I already told it, Duncan told it about it. If you have very elongated conductor and your primary field electrical field is directed along, you create extremely strong galvanic part of the field. Extremely strong. Now, and there are many calculations, there are many things. So that's what behind of many formulas which you can find in many books about this part of it. Now, few words about magnetotelluric soundings as example of influence of this part. Two examples. No, three. Example number one. You have, let us consider, deep magnetotelluric sound. They are still used by universities for study of deep layers. Then I will give you example from which is important for exploration, is what is the role time domain sometimes. This matters. Now, example number one. I have 3-layer medium. Please remember it's not exploration. So model could be unusual for you. So rho 1, H1. Now, extremely resistive, almost infinity thick layer. And then very, very good conductor. Even you can understand what is the purpose of this resistor. As function of wavelength, so that's wavelength, high frequencies, low frequencies, over H1 has the following form. That's apparent resistivity over rho 1. High frequencies, we get rho 1. Then zone S, resistivity increases. Then when wavelength becomes such, wavelength not in point propagation, skin depth becomes very, very, very great, we start to feel good conductor. So, I tried my best to tell you, but I didn't tell you everything. I should stay for a little longer. So that's this is the zone S. What zone S means? It gives you conductance, S of first layer, S1, H1 over rho 1. Clear? At least believe me. Please believe. Now, but it's possible to grasp this fact. Why? Because there is a range of frequencies when currents uniformly distributed in this layer, and this layer could be few kilometers thickness, behaves as a foil, as a infinitely thin sheet. The same we have in time domain when we discuss overburden in Sed. Now, then there is a period or frequency, as you wish. I did mistake, not mistake, but I would like to emphasize here, instead of this unpleasant lambdas, please imagine square root of period. So period of oscillation. So period Small period, high frequency, very large period, low frequency. So then there is a moment when we start to feel very good conductor. Then the longer period, the stronger influence conductor. It turns out in log scale it's a straight line. And this straight, moreover, there is a beautiful feature of this part of the curve, which was the main attractive force for using MT for deep soundings. What is the feature? It's called zone H. H, where H, that's rho 1, that's H2. So H equal H1 plus H2. It's very useful. That's the main goal for this kind of model MT. Why? Because if you have very good conductor and you reached this part of the curve, then you get depth to the transition from high resistive to very good conductor. Even theory is so simple that ratio of electrical field over magnetic field impedance simply equal omega mu H at this range. So you measure electrical field, measure magnetic, take ratio, divide omega mu, and you got total thickness. Awfully attractive. Now let us assume that we have that's ideal situation which we would like to have. However, there are sometimes, not sometimes, very often, lateral changes of resistivity. Suppose there is a host block with high resistivity, relatively resistive medium rho 0. Here rho 1, here rho 1, that's host. And we measure here. So we measure our electrical field. Let us discuss if electrical field, for example, in this direction. Then we measure magnetic field, By, Ex. That's axis X. What would happen in this case? Electrical field has this direction. Therefore, at interface, our lovely electrical charges arise. If it's more resistive medium, it's a positive charge. Here, negative charge. This electrical charge is proportional electrical field. Remember, I wrote you this expression, 2 epsilon naught, K1, 2, En average. Where exactly we measure? At this area. So electrical field due to these charges has this direction, from plus to minus. So along with our plane wave, we will have strong electrical field. And all our curves go up. And instead of this business, we will get this curve. And it turns out, so all time, because regardless of period, you have electrical field. You do have. Therefore, you have charges all time. And you measure your electrical field, which you measure equal E naught plus secondary electrical field due to charges, galvanic. If this field decreases, secondary decreases exactly the same manner because charge is proportional to this field. So apparent resistivity curve shifted up. And it turns out that it could shift it 5, 10 times up. So therefore zone H will give you depth to the low boundary 10 times more. So now please imagine you measure here in apparent resistivity. You measure here apparent 1, 2, 3 apparent resistivity. So when you are far away from this inhomogeneity, you will get the same boundary 5 kilometers. So let me plot the profile. So suppose we are interested by only low boundary. Understandable? Low boundary. The same I can draw for first boundary. So I have boundary, boundary, boundary in the same level, H1 plus H2. Now I interpret this point. What happens with depth? It goes down. And again normal. So I have to interpret what is interesting. Shape of the curve remains almost the same. So it's very nice. It's not distorted. So it looks like a 3-layer curve, apparent resistivity. And a great depth I got syncline. But no syncline. The same flat interface. But what happens? Beneath our foot, there is an inhomogeneity. That's an effect called static effect. In 82, I described in my book Magnetotelluric Soundings in detail this effect. It's a dangerous. That's example what happens in magnetotelluric method when electrical field perpendicular to the horse. We don't know where is this inhomogeneity. It could be not horse. It could be, for instance, some small lateral change of resistivity. For example, suppose there is volcanic cover, as there is at Columbia Plateau in the United States, beneath sediments, basement. Volcanic cover is a very serious first obstacle for using seismic because many reflections and high noise because energy goes from top to the boundary, it sediments, then back, and attenuates very slowly. So it's difficult to get signal from basement. So in order to avoid this problem, magnetotelluric was used, but it turned out also trouble because in volcanic cover there are many spots of low resistivity, for example, clay or any other surface formations. They do create extremely strong effect. Shortly, you do have lateral changes, but depth few dozen meters, but it results appearance false anomalies. You cannot do practically anything. So it's simple to say, sorry, we are in trouble, instead of inventing false anomalies. So that's the main reason, one of the main reasons why exploration refused to use more magnetotelluric patterns. Let us stop here.